Hey, what's up, guys? This is Sean here again. So, LeetCode number 1987, number of unique good subsequences. Okay, so you're given like a binary string binary, right? A subsequence of binary is considered good if it is not empty and has no leading zeros, right? With the exception of zero itself, right? And then you need to find the number of the unique good subsequences of this binary string. Okay, so basically, a while back we uploaded a video for number 940, right? So this one is like it's in the same category with that one. It's the same kind of DP problem where you need to get the total number of unique subsequences. Okay, so that's why we're gonna use that one as a base to solve this problem, right? So let's take a look at some examples here, right? So we have this one 001 here. The answer is 2 because there are like only 2 unique subsequences, right? So we have this one, but since 0 and 0 they are duplicated, and we only need the unique ones, right? And here's the constraints, right? Like 10 to the power of 5. Okay. So if you guys do remember how we solved that problem, right? So we have like what? We have a dp state transition function here, right? Where the dp I, right, equals to what? Equals to 2 times dp I minus 1, right? Subtract the duplicate, right? So a little bit about this state transition function is because let's say this one is a. Oh, so first, where did we get this 2 times dp I minus 1? This is because for if everything is unique, right? And then basically every time when we add a new numbers here, a new letter here, so the total number of subsequences will be doubled, right? Basically, if we have A and B, right? So the total subsequences will be A, B, A, B, and empty string, right? If we add a C here, so it's going to be what? Going to be 4 times 2, right? That's why, because we're going to add C to everything, right? So basically, so 1 4 is from the previous from all the subsequences which does not don't include C, and another 4 is our subsequences which include C, right? Which is going to be AC, BC, ABC, and C, right? And then if so on and so forth. If we had a D here, we need to do another 2 times here, right? So that's why. So that's how it works, right? So that's how we get is 2 times dp I minus 1, and this duplication straightforwardly enough is when we have a duplication, right? So when we have A here, okay, and then another A here. So basically, the closest A, right, with the current A will be the ones we're looking for. Let's say this one is J, okay. In that case, this duplication will be equals to dp of what? J minus 1, right? And why is that? Because from here, right, from this one, let's say we have like a bunch of like we have let's say 4 total unique subsequences for this part, right? And this 4 plus A will be the ones will be the a new subsequence, right? And then from here to here and from here to here, right? So those 2 routes or those 2 paths are duplicate, right? Because it doesn't really matter, because from this space, if you add A here or if you add A here, right? They will result with the same subsequences. That's how we find the duplication, right? Where we find the A here, right? Find the closest A starting from this A, right? And then we will basically use this dp of j minus 1, right? Because this is the many, so the dp j minus 1, j minus 1 is here, right? So the total subsequences ending with j minus 1 will be the ones that got duplicated, right? Okay, cool. So that's the basic idea for this kind of unique subsequences problem, right? And here is the dp transition function. And when it comes to this problem, right, we just need to do some small modifications, right? So what do we have? We have 0 and 1, right? So for example, right, we have, let's say we have 0, 0, 0, 0, 1, 0, 1, 0. It doesn't really matter. Okay. So the tricky part for this problem is that we don't allow any leading 0 values, right? So what does it mean? It means that everything before seeing a 1 will all be 0, right? So basically the dp of this is dp, right? So the dp of this one will be 0, 0, 0, 0 until we see the first one. That's when we do have 1, right? Okay, no. So at this time, we are like we're not considering this 0, because for this one, we can simply just check this one in the end. So now we're simply just removing, not considering the 0 itself. That's why it's all the zeros before seeing the first one doesn't make sense, right? Because there will be none in our case, right? And when we see the first one, that's when we know, okay, so for this one, the dp of this one is obviously 1, right? And after this, right, and after here, we can use this dp state transition function, right, to get everything starting from 1, right? So the reason being, the reason we start looping through from here instead of here is because when we do the dp here, right? So this 2 times dpi minus 1 means that we can either include this one or don't, right? So let's say if we start from 1 here, it means that we can either include this one or we don't include this one. If we don't include this one, okay, then what does it mean? It means that, let's say for example, we're at here, right? And then if we don't include this one, then it means that we could have like 0 and 0 here, right? And which does not make sense in our case, because in our case our DP definition means that it's a valid subsequence, right? That's why for this problem, since we have this kind of no leading 0 constraints here, that's why we'll start looping through this dp from here instead of here. Okay, and this dp of the first one will be our base case, right? Okay, cool. And yeah, so that's it, right? I mean, we just need to find this first one, and then we start from this one, this I plus 1, right? Oh, and since we're always making sure we already have 1 at the beginning, right? In this case, when we create a DP array here, right, we can simply use length n instead of n plus 1, right? So the reason we were using n plus 1 is because we are trying to make sure this I minus 1 will always be in the range, right? But in our case, since this I will always be starting from at least from 1, right, instead of 0, because we have 1, we're making sure there's 1 at the beginning, right? And that's why we can simply use n size. Cool. So let's start coding that, right? So what do we have? Let's find that index, that starting point, right? So we have s equal to 0, and then n is going to be the length of the binary, right? Binary. Okay, and then let's move this one to the top. So while s smaller than n and the binary of s equal to 0, right? We keep moving s forward. Okay, and then here we can do a sanity check. Basically, if the s is equal to n, it means that all the digits are 0, right? So what does that mean? It means that there's only one unique subsequences, which is 0 itself. Okay. Otherwise, we can create our DP here, right? So that's the, like I said, in this case, we can simply use n here because we know the DPS, right, will be 1. Okay. And when we do the for loop here, right, we'll start from s plus 1 to n. Okay. Okay, and in this case, since we need to know the last either 0 or 1, right? We can just create 2 variables, right? To tell us where is the last 0 and 1, right? Comparing to 940, in that problem we have 26 English letters. That's why we use like 26 length of array. But in our case, we only have either 0 or 1. That's why we only need 2 variables here, right? So same thing. So we have j, right? So j is going to be the last 0, right? If the binary I is equal to 0, okay, else last 1, right? So that's basically the last either 0 or 1's index, okay? And then the duplication will be duplication equals the dp of j minus 1, right? Like we have already talked about. And but we need to have like a sanity check only when the j is greater than 0, else 0, because we have this dpi is equals to 1, right? So if j is equal to 0, right, it means that, sorry, yes, if the j is equal to 0, it means that we have never seen this either 0 or 1 yet, right? Okay, yeah, because we only update this last 0 or 1 whenever we see we see another like 0 or 1, right? But since we're making sure so this I will at least start from 1, right? Then this 0 will not confuse us, because as long as we see either 0 or 1, it will be they will have the index at least starting from 1. That's why we can use 0 to check if we have seen either the 0 or 1. Okay, otherwise we need to set 0. Okay, and then for the DPI, we just copy and paste that state transition function, I minus 1 times 2 minus dupe. Okay, and then don't forget to update the last 0 and 1. So if the binary of I is equal to 0, right, we do the last 0 equals to I, right, else last 1 equals to I, right? And then okay, so now let's handle this exception 0, right? How can we handle that? Easy, right? We simply just check if there's any 0 exist in this binary. Okay, so has 0 equals to 0, right? If 0 in the binary, right, and then has 0 equals to 1. Okay, and then return the dp of I minus 1 plus has 0. Okay, and then divided by the mod. We need the mod here. Plus 7, right? So here, right? So if you guys remember, when we solved the 940, we did what we did. We did like this plot and -1. And why was that? Because for that problem, we are like we don't allow empty subsequences, right? But for this one, it's fine. Why is that? Because remember, we start from okay, right? We start from here, right? Which means it's guaranteed that even though there's nothing here, right? There's still be one at the beginning. That's why there's no empty subsequences issue here. We need to subtract, right? So we can just get everything from here because we have one at the beginning, right? And then we simply just add this has 0, 1, right? Run it, submit, right? Cool. Yeah, so that's it, right? Because time complexity for this one is O of n, right? We only have one for loop here, and then yeah, that's it, right? Cool. I think that's it for this one. Because I think there are some other like solutions. I mean, who has the much shorter code, right? From the discussion board. But this one, in my opinion, it's a more typical way of solving the DP problems, especially since we have that 940 as a base, right? So why not just follow the same pattern to solve this one, right? Where we just get the total subsequences, right? And then we subtract the duplication ones, right? So for this one, the difference is that we have to somehow tweak this algorithm a little bit, where we start from 1, right? And then we use that algorithm to apply everything after 1 to make sure we will not have this leading 0 issue, right? And then in the end, we will just add that 0, 1 back if there's any. Cool. I think that's it for this problem, and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.